Hello students, welcome back to chemistry class. Let me ask you something. Have you ever seen a piece of rock salt sparkling in the sunlight or admired the beauty of snowflakes under a magnifying glass? Each of these owes its beauty to crystals. But what exactly are crystals and how are they formed? When we prepare a hot saturated solution and then cool it, the excess solid doesn't just separate randomly. Instead, it organizes itself into definite geometric forms, and this process is called crystallization. The solid particles formed are called crystals. By definition, crystals are homogeneous solids in which atoms or ions are arranged in a repeating three-dimensional pattern. They are bounded by flat surfaces known as faces, which meet at sharp edges and angles. Some common examples around us include table salt, which is sodium chloride, written as NaCl, sugar with the formula C12H22O11, and the beautiful blue copper sulfate pentahydrate crystals, written as CuSO4.5H2O. Now, not all crystals look the same. Their external shape depends on the internal arrangement of particles. Nature provides us with 6 basic crystal systems, and each is fascinating. Take sodium chloride, for example, it forms cubic crystals. Sulfur, with its molecular form S8, forms rhombic crystals. Then there are tetragonal, monoclinic, triclinic, and hexagonal systems, each having characteristic angles and faces. What's amazing is that the shape we see under a magnifying glass is simply a reflection of the symmetry in the way atoms or ions are arranged inside. So, in chemistry, crystal shape is really a window into the atomic architecture of matter. Let's go deeper into the process itself. Crystallization is defined as the separation or deposition of crystals from a hot saturated solution of a substance when it is cooled. Remember, a saturated solution is one that contains the maximum amount of solute dissolved at a given temperature. As the solution cools, the solubility decreases and the excess solute cannot remain dissolved. It separates out as well-defined crystals. This isn't just a lab trick. Crystallization is a key purification method in chemistry used to obtain pure solids. Think of how we prepare crystals of alum, copper sulfate, or potassium nitrate. All of them rely on this very principle. But students, here's something important. Not every attempt at crystallization gives you shiny, perfect crystals. Certain conditions must be met. The hot saturated solution must be cooled slowly so that the particles have enough time to arrange themselves into definite, repeating patterns. Slow evaporation of the solvent helps in the growth of large and pure crystals. If cooling is done too rapidly, instead of crystals, we get amorphous solids. These are shapeless, irregular solids without definite geometry. Glass and pitch are common examples of such amorphous solids. That's why, in order to get large, beautiful crystals, controlled crystallization is essential. Now let's bring this to the lab bench. Suppose we want to prepare large crystals of potassium nitrate, which is KNO3. Step 1 is to prepare a saturated solution of potassium nitrate at about 90 degrees Celsius and then filter it to remove any impurities. Step 2. Allow the clear filtrate to cool and you see small crystals forming at the bottom. Step 3. Tie a small seed crystal, that is, an already existing tiny crystal of potassium nitrate, with a thread and suspend it in the cooled solution. Step 4. Cover the beaker with a muslin cloth to prevent dust from entering. Over time, more and more solute particles deposit onto the seed crystal and gradually a large, well-formed crystal of potassium nitrate grows. This simple yet elegant procedure shows us how nature builds order from a seemingly ordinary solution. After a few days, when you check the beaker, what do you observe? A beautiful, large crystal of potassium nitrate has formed. The conclusion is clear. When a hot saturated solution cools, excess solute particles come out of the solution and arrange themselves layer by layer on the seed crystal, leading to crystal growth. The slower the cooling and evaporation, the larger and purer the crystals we obtain. This experiment not only confirms the principle of crystallization but also demonstrates how we can control conditions to achieve purity in chemical substances. So let's wrap this up by looking at why crystallization matters beyond a classroom. In daily life, crystallization is used to purify salts such as table salt, sugar, and alum. In industries, it plays a huge role in preparing silicon crystals, which are the backbone of semiconductor devices in your computers and smartphones. In medicine, crystallization ensures the purity of drugs and pharmaceuticals, making them safe for use. And in nature, crystals are everywhere, from the intricate beauty of snowflakes to the brilliance of gemstones like diamond and ruby to the natural minerals like quartz. So, to sum up, we've explored what crystals are, their shapes, the process and conditions of crystallization, an experiment to prepare potassium nitrate crystals, and their significance in the real world. I hope this session helped you see how crystals are not only aesthetically beautiful but also central to chemistry, industry, and even technology. Until next time, remember, every crystal you see is chemistry's way of showing order in the universe. Catch you in the next class with more fascinating insights into the world of chemistry.